Whether it is a swimming fish or a hovering dragonfly, flow visualization techniques help scientists and engineers shed light on important fluid dynamic phenomena that would otherwise be invisible. This is a 3-link swimmer, a machine designed to swim at low Reynolds number, a realm where fluid viscosity dominates. Microscopic organisms such as bacteria and protozoans swim at low Reynolds number. These swimmers must propel themselves not by generating momentum, but by fighting viscosity. When we place the swimmer in a tank of viscous oil, all we can observe is the swimmer's position and the fact that it does indeed move forward. By placing lines of colored dye into the fluid, we are able to trace the path of the fluid as the swimmer makes its way across the tank. Another way to trace fluid motion is to disperse tiny particles which align themselves with the fluid when it shears. When the swimmer is placed in a suspension of these particles, we are able to see where the fluid is shearing the most. At high Reynolds number, animals like the water strider use fluid momentum to create thrust. Water striders are particularly interesting in that they are supported on the water's surface by surface tension. For a long time, scientists disagreed on how they were able to transfer momentum through the surface without breaking it. In 2003, John Bush, David Hu, and Brian Chan used dyed water to show that the striders transfer momentum using vortices rather than waves. Before this point, it was assumed that the waves had the most significance in the strider's mode of locomotion. Particle image velocimetry is a method where many neutrally buoyant particles are randomly distributed into the fluid. A laser sheet illuminates one section of the experiment to be picked up by a camera. A computer tracks the motion of the particles, and the entire velocity field of that section can be determined. Here, the fluid motion around a flapping fin is analyzed. Polarized light can be used to visualize flow as well. This is a dilute solution of water and tobacco mosaic virus. The flow of fluid is made visible using polarized light. The virus, which is harmless to humans and fish, has a long rod-shaped structure which aligns to flow much like the particles used with the 3-link swimmer. Because the virus particles are microscopic, we cannot use them to see the flow using ordinary light, but polarized light makes them visible. Most sources of light emit light waves that have random orientation. When the light is passed through special filters, it becomes polarized, which means the waves are oriented in one direction. The particles block or transmit the polarized light depending on their alignment. This visualization method enables researchers to see the vortices in the wake created by the fish while it generates thrust. These and other techniques have helped scientists to understand a myriad of fluid phenomena and have enabled engineers to develop better fluid machines.